All right, 3.1, we're going to look at the derivative formulas for powers and polynomials. All right. So first, let's start with linear function. Right. If you have a flat line, a constant function, right, then it's not increasing nor decreasing. Then in terms of slope, it's going to be 0, right? Now, a constant function. Constant function, not increasing or decreasing. Therefore, f prime is always 0. Now, if you have a linear function, right, in the form of the slope intercept, right, mx plus b or b plus mx, then we know that the derivative of function represents the slope. Now, since the slope for a function, for a linear function is always the same, then f prime is just going to be equal to the slope m. Right, so for example, if you have this notation, it means the derivative of this expression right here is going to be -3/2, right? Because -3/2, that is the slope of the function, which appears right before x, right here. Okay. Another way to write this is we can say that we have a function which is linear, 5 minus 3/2x. Then f prime will be the slope of the function, which is -3/2. Next, we have some property of a function, right? If you have a constant multiplying a function, you can actually bring that constant out of the derivative, right, and put it on the outside, and just multiply c by the derivative of the function. Same thing with sum and difference. The sum of the derivative of a sum of function is the sum of the derivatives. Same for difference. Right? So you can take derivative of f and g separately and then add them together or subtract them together as you wish. Next is the main rule, the power rule of a polynomial, right? So this is the formula you need to take the derivative of a power function. All you need to do, oh my gosh, is bring down the power n and subtract it the power by 1. All right, so let's do an example. Let's say I want to take the derivative of the function x squared. Now, all you do is you take the 2 and put it in the front, right? And then copy down the x. And then in the power, you're going to decrease the power by 1, the original power by 1, right? So that gives you 2x, right? That's what we have here, right? You have the derivative, you have the original function x squared and the graph of the derivative. All right, and you can look at the third one. So we have g of x. I'm gonna try a different notation, right? So g of x is x cubed. Then g prime of x is the same thing. We're taking the derivative, so bring down the power 3, and then x, and decrease the power by 1. So 3 minus 1, and then you will have 3x squared. Okay. And that's how you take the derivative. That's how you take the derivative of a power function, x to the power of n. Now let's look at some more example. All right, so starting with part A. All right, so we want to differentiate all these four. So differentiate, this word also means take the derivative. All right, so we want to take the derivative of capital A of t, which is 3 times t to the 5th power. And then we know that to find a prime of t, we need to differentiate everything here with respect to t. Notice that I'm not writing dx in the denominator anymore. I'm writing dt because the t corresponds with the independent variable. All right, so d dt of 3 times t to the 5th power. Now from earlier, we know if we're multiplying by a constant, we can actually bring that constant and put it on the outside. So it's 3 times d dt t to the 5th power. All right, so 3 brings down. Now to take the derivative of a power function, all we need to do is bring down the power to the front, so 5, right? And then times t. Subtract the original power by 1, so 5 minus 1 will be 4. Okay, and then you can multiply the 3 back in here. So 3 times 5 will be 15, and then t to the 4th power. Okay, so let's try part B. We have r of p is equal to p to the 5th power plus p to the 3rd power. And then r prime of p will be to differentiate everything with respect to p. All right, notice I changed the denominator as the independent variable changes. All right, so of p to the 5th power plus p to the 3rd power. Now we know that if we are taking the derivative of a sum, we can actually take the derivative of them separately, right? So we can write this as d dp of p to the 5th power plus d dp of p to the 3rd power. All right, and then we can just look at each one of them separately. All right, so hopefully by now we have a better idea of what we're doing. So bring down the power to the front, 5, and then p, decrease the power by 1, which will be a 4. And then plus, bring down the power 3, and then p, decrease the power by 1, which will be a 2. And that's it. That's your final answer. And next, let's look at the other two. All right, part C, we have f of x is equal to 5x squared minus 7x cubed. All right, so now I'm actually going to show you a faster way of doing it to find f prime for polynomial. Okay, so we know they're separate, so we can actually look at them separately. All right, so for the first part, all you need to do is bring the 2 down, right? So bring the 2 down and multiply with the 5. So 2 times 5 will give you a 10, right? And then write x, decrease the power by 1. So 2 minus 1 will just be 1 to the 1st power, minus, and then we're going to do the same thing here. Bring the power 3 down, multiply by 7. So 3 times 7 will be 21. And then x, decrease the power by 1. So 3 to 2. 3 minus 1 will be 2. All right, so here we have it. F prime of x is 10x minus 21x squared. Now go ahead and pause the video and try part D on your own. All right, so part D, we have g of t is equal to t squared over 4 plus 3. And we can do the same thing here. Before we move on, I actually want to rewrite this as t squared over 4 plus 3 times t to the power of 0. Okay, so g prime of t, bring the power down. So 2 times 1 over 4, that will give you 1/2. Right? And then t power 2 minus 1 is 1, so we don't have to write it. Now next, we look at plus. We're going to bring down the 0. So 0 multiplied by anything is 0, right? And then we don't actually have to worry about the power because it's 0, right? So that concludes our derivative. It's just 1/2 t, right? So the derivative of a constant is always 0. All right, our next example, we have a function y equals to x cubed plus 2x minus 5x plus 7. And our goal is to find the tangent line right here. All right, we want to find the tangent line and the equation at x equal to 1. All right, so first we need to find the derivative at x equal to 1, right? That will give us the slope of the line passing through x equal to 1. Okay, and then 2, use slope intercept form to find the equation. Okay, so that's basically what we're doing. All right, so first part, let's find the derivative. So y is equal to x cubed plus 2x squared minus 5x plus 7. All right, so dy dx, you just need to take the derivative of each term separately, and hopefully now you have a really good idea of what to do. All right, so bring down the 3, decrease the power by 1, plus bring down the 2, so 2 times 2 will be 4, decrease the power by 1. Bring down the power 1, so which is minus 5, and decrease the power by 1, x to the power of 0 would just be 1, so that will be your constant term. And the derivative of a constant is always 0. All right, so that is our derivative. Let's say f prime of x. All right, now we need to find out what f prime of 1 is. All right, that will tell us the slope of the line passing through x equal to 1. All right, so f prime of 1 is equal to, plug in 1, you get 3 plus 4 minus 5, which is a positive 2. Okay, so that will be the slope of the line passing through the point when x equal to 1. Right, so we have found the slope of this black line right there. All right, next, let's just look for the equation of the line. All right, in order to find the equation of the line, first we have the slope, and we also need a point on the line, which would be this point. Right, to find that out, you just take x equal to 1, plug into the original function y, and then you get 5. So the point 1, 5 also lies on the line. Right, so you have a point, and then you have the slope. We can begin step 2. Slope intercept form is in the form of y equals to mx plus b. Right, so all we need to do is fill in everything we know and then solve for b. All right, so slope is 2, y is 5, x is 1 plus b. All right, then that's just a 2, so subtract the 2 to the left hand side, we get 3 is equal to b. All right, and then we have everything we need. Y is equal to m, that's the slope, 2x, plus b, b is 3. Okay, and that is the slope of the tangent line. Now that's the equation of the tangent line. Equation of tangent line. Okay. All right, next we have problem 74. A ball is dropped from the top of the Empire State Building. The height y of the ball above the ground is given as the function of t, y equals to 1250 minus 16t squared. Now, before we move on with this example, there is something we need to talk about. All right, so this is something called the PVA type of problem. That stands for position, velocity, and acceleration. Okay, now position is usually your original function, p of t, with respect to time. Right, so in this case, y is actually our position function. It tells us about the height of the ball t seconds after it being dropped. And velocity is how fast the ball is dropping, right? And acceleration, as we mentioned earlier, is the change of velocity, right? How fast is it increasing? How fast is the speed increasing? And something nice is these three values are actually related. If you take the derivative of the position function, you get the velocity function. And then if you take the derivative of the velocity function, you get the acceleration function, which is the second derivative of the position function. Okay, I think we just need velocity and position function in this case. All right, so A, find the velocity of the ball at time t. What is the sign of the velocity? Why is this expected? Okay, so we know that position function, which is y, that is 1250 minus 16t squared. And then if we take the derivative of it, p prime of t, which is dy dt, the derivative of constant is always 0, right? So we can ignore that. And the second one, we bring down the 2 multiplied by negative 16, we get negative 32. And then subtract the power by 1, we just have the t. Okay, so let's answer the rest of the question. It says, what is the sign of the velocity, right? So negative 32, t is time. Time is always positive. So this whole thing is actually negative. Okay, why is this expected? So think about this for a second. We're talking about velocity. So a negative velocity means it's going in the opposite direction of positive, right? So usually if it's up and down, up means positive velocity and down means negative velocity. So it's negative because ball is traveling downward, right? If it's down, then velocity is negative. If it's up, velocity is positive. Okay. All right. Now let's look at part B. When does the ball hit the ground and how fast is it going at the time? Give your answer in feet per second square, feet per second and in miles per hour. All right. Now I'm going to just do the first part of part B. Okay. So when the ball hit the ground means the position is 0. Right, so hit the ground means 0 foot above the ground. Right, so we have to set this position function equal to 0. Right, so 1250 minus 16t squared is equal to 0. That is 1250 is equal to 16t squared, and t squared is equal to 78.125. And then when you take the square root of that, you get plus or minus 8.84. Now, remember that t is in terms of time, so we only need to take the positive one because time is positive. Right, so t is 8.84 seconds. It means after you drop the ball, when you drop the ball after 8.84 seconds, the ball is going to hit the ground. And next, we want to know how fast is it going. So all we need to do is take this t, 8.84, plug it into the velocity equation, a velocity function, and then evaluate, and we will see what the speed of the ball hitting the ground is. All right, so t equal to 8.84 seconds, and we know that the velocity function p prime of t, which is the velocity function, is equal to negative 32t. So velocity at 8.84 second is going to be negative 32 times 8.84, which is about negative 283. right? Okay, so this is going to be feet per second, right? That's the original unit that we're given, right? So feet per second. So when the ball hits the ground, it's actually traveling downwards at negative 283 feet per second. Of course, this is not including any air friction and any sort of other force that's stopping the ball from falling too fast. All right, and then let's convert that into miles per hour. All right, so to convert from feet per second to mile per hour, all we need to do is take negative 283 feet per second, multiply by the conversion here, 15 over 22 miles per hour, which will be approximately negative 193 miles per hour, which is very fast, right? Almost, it's also as fast as an F1 race car, right? And that's it, right? So let's recap this problem a little bit. First, to find the velocity, we just take the derivative of this, right? So dy dt will be velocity. And then to find the ball hitting the ground, we take the original position function, set it equal to 0 because it's 0 feet above the ground. And then take the time t, which is 8.84, plug it into the velocity function to find the speed. Right? And that's part B. Okay, all right, that's 3.1. Thank you guys very much.